Hey. Hi. So hello, everyone. Today, we're going to talk about Project Slingshot and ZkVM. My name is Oleg Andreev, and I work at Stellar on this project for some time already. So I'd like to give you an overview why we do that, how we're going to use it, and why is it interesting. So let's do the time check. All right. So the problem that we have is we know about the blockchain. So how do we do the blockchain that protects the private information while being in the public, right? It's a public system that's fully auditable and transparent. But yet we do the private transaction in it. So effectively, we want something like Ledger with TLS. So there are kind of two major components to it. One is the confidentiality part. So for this, we need some sort of encryption for our balances and accounts and amounts that we transfer. And since it's a public system, we need a public verification mechanism for proving that the hidden transfers actually correct and respect the kind of balancing equation that people, when they're transacting, they don't create the money out of nowhere. So we need some sort of zero knowledge proofs in our technology stack. And the third important component is that some customization mechanism. Why is that? The blockchains are essentially consensus systems. They work best when they're mostly decentralized, deployed widely, and as many applications and users run them and execute the rules and check the transactions. And this means that it's very hard to upgrade the system with new features or improvements. So we need to, on one hand, to make it as simple and focused as possible so it's not buggy, but at the same time, we want to build some interesting features around the system, like from smart contracts to whatever, decentralized applications to improve the security of people transacting in this new environment. And one way is to just roll out network-wide upgrades, which is as hard as it is decentralized. Or on the other hand, foresee some customization points so people can build things on top of it without changing the underlying rules. So this is where the VM part comes in. We need some sort of programmability for our system, and if it's programmable, it means that there are programs, and it means that there is some sort of virtual machine that is going to execute those programs. So this is where the VM part comes in. Now, what is Slingshot and how does it relate to ZkVM? So Slingshot is an umbrella term for the entire suite of libraries and protocol implementations that include not only the kind of most interesting part, the transaction format, the zero knowledge proofs, and the programmable conditions, which is ZkVM, but also all the auxiliary cryptographic libraries, such as signature schemes, multi-signature things, the Merkle tree implementations, all the way to the entire blockchain system, where the blockchain state machine as a separate protocol implementation, the peer-to-peer networking stack, and higher order application protocols, such as the mechanism behind the accounts, the protocols for synchronizing wallets, doing payment channels, order books, and all these kind of things that could be built on top of the on top of the core blockchain system. So this whole thing is called Slingshot, and it all exists in a single GitHub repo where the development happens. Now, what's kind of interesting about ZkVM and the Slingshot is that it's a highly modular design. Why is it important? This is not a single application that has a specific way of using it. It's more like a collection of libraries that we can flexibly figure out how to deploy and roll out in the best manner. So we can build a sidechain, or we can use it as a private ledger, or we can use it as both. The cryptographic pieces are composable, so we can attach the off-chain proofs to our transactions. So for instance, we can offload some computational cost from the network by building some intra-party proofs about payments, for instance, some notarization or like zero-knowledge audit schemes completely outside of the blockchain, so we don't have to load the entire network with this computationally heavy problem. We can use the full node as a library embedded in the greater application that, for instance, does some interesting indexing of the transactions. And we can decide how big the node should be, how much data should it store. For instance, the UTXO state compression scheme allows us to have very little minimal state at the cost of a little bit more bandwidth overhead. And you can decide whether you just have this very compact full node embedded in your wallet, or you have even lighter wallet, or you build a completely standalone application running on a cluster, for instance, with as much data storage as you possibly can, because you want to provide as much service to the very light applications. And this is why the whole project is designed to be modular from the beginning. Now, specifically, ZkVM is a transaction format that sits on top of the networking part and the consensus mechanism. And on top of ZkVM, then you can build your custom application protocols. So what does it mean to say that ZkVM is a transaction format? So in other words, ZkVM is a fancy parser. If you think about Bitcoin or Stellar or Zcash, the transaction format in those protocols is more like XML. So it's some kind of hierarchical structure with lists of things that contain other things that describe declaratively the flow of assets. In contrast, Ethereum is much more programmable, but the transaction format is more like a remote procedure call, where the transaction just sends a message to the network, and then you have the global state with some programs loaded into that state that can be invoked and do some operations, do some mutation to the state, and the transaction is simply signed message into this global computer. And ZkVM is neither of those two things. It's more like a PDF. So it's sort of a declarative format, but at the same time, it's an executable little language that you run through the VM that is sort of like a parser that executes the commands, does some local operations to determine what changes to the state should be made. So to kind of explain this better, this is the quick overview of the data model in ZkVM. So you have transactions, and transactions are objects, these little files that transfer assets from inputs and outputs. And they can also issue arbitrary assets because it's a multi-asset environment, right? Just like Stellar. So this is how the asset flows from inputs to outputs. And the outputs are actually the objects that we call contracts. They have a predicate that kind of locks some content inside the contract and provides conditions to unlock the contents. And the contents are called a payload, and it's actually a list of things. And those things could be either values that are so-called linear types, the things that you can move around but cannot duplicate, which are the assets themselves. or some data parameters. So your contract is this collection of values and data that can be locked into this container by a predicate. And the simplest way to think about the predicate is the public key, right? So you say whoever owns the corresponding private key can unlock the values and then decide what to do with them. And you unlock by showing the signature on a transaction. So you have a transaction that says, I want to spend this value in such and such way. You have to provide a signature that authorizes you to unlock that contract. Or the predicate could be a little subprogram. So you have to run the program, meaning that the VM will run the program and check additional conditions that are described by the program before deciding to unlock the values. And you can combine both of them with a scheme we call taproot. It's a like Merkle tree of programs and public keys. So you have the flexibility to decide things like you can either have multiple parties sign together the contract, or they could choose individually whatever branch they want to execute. So this gives you a lot of flexibility in terms of pre-programming different conditions that unlock the money. And it's a little bit even more flexible because you can not only pre-program some conditions or provide a signature over a transaction, but you can also provide a signature over new conditions. So you can decide some program later and then sign it, and then that program will be executed. So this gives you infinite ability to do some interesting multi-state schemes while having a pretty simple design. So how does this all work inside the VM? Again, transaction is just a program, like I said, like a PDF file. So in our case, it's has just a little bit of metadata. It's a program that also has a zero-knowledge proof. And we'll show in a second how this proof applies. So what happens when you want to verify a transaction? You instantiate a VM, and by you, I mean the node that verifies the transaction. It instantiates the VM that is completely ephemeral. It means that it's not some sort of globally running VM like a Docker container kind of thing. It's like an instance of a parser for this specific transaction. So it's very lightweight. You create it just for a single transaction. You load the transaction into this VM, and it works as a simple stack machine. So it has a simple stack. It's not Turing complete, so it has a predictable performance. And the goal of the VM is not only to provide you with the ability to customize your conditions, but it also enforces the network rules. So the operations that it executes, they're also checking that you don't duplicate money, that you respect the rules of the network and don't break them. So what VM does, it runs the program, and then as the program is running, it's compiling on the fly a thing that we call a constraint system, which will be used for the zero-knowledge proof. So the constraint system is effectively just a list of linear and multiplicative equations that check that, for instance, the some amount should equal some other amount or should be subject to a certain formula. But the cool part is that this constraint system works in zero knowledge, meaning that those numbers in the formulas that you're manipulating, they're all can be encrypted. And so your program can manipulate these encrypted values and require that they conform to a certain formula. And as a result of execution of the program, you will have this sort of a matrix of constraints that builds this constraint system. And after the program finished executing, then the verifier runs the zero-knowledge proof, like VM checks that the proof is correct for this constraint system, which proves that whoever knew these secret keys that encrypted those amounts correctly combined them. So if there was a smart contract saying that a couple of values must correspond to a certain formula, then these values being secret, they're still correctly constrained by that formula. So this is the job of the zero-knowledge proof. And the VM does that in the end of the program execution. And finally, all the effects in the VM are fully local. They don't affect the global state. So it's allows you to evaluate all the transactions independently from each other and verify in parallel. So how do we even do the effects? So all these inputs and outputs are actually recorded in the transaction log, which is simply a list of effects that should be applied to the blockchain state. And once we've run the program and verified the zero knowledge constraints, then we simply take this log, this list of effects that are effectively saying that you have to erase certain inputs and create certain outputs, and then we apply them to the blockchain state. And this is very lightweight operation that can only fail if you're trying to double spend the same output twice in two different transactions. And if it happens that the second transaction tries to spend the same input, then it will fail in the very end of the application stage. But this is the only stateful operation in the system. Now, how do instructions look like? Think of this as a stellar operations. In stellar transactions, you have a list of operations that you could do, but they're more like a list of things that are not really working with each other. They just enumerate what you want to do in a transaction. For instance, send money from here to there, or open offer, or create an account, things like that. So in a similar vein, ZkVM has instructions that are high level, like in Stellar. They're high level operations. They don't they are not like assembly language low level operations that just manipulate bits. They manipulate values. They manipulate contracts. The high level concepts, but they are all composable with each other. So, for instance, you can instantiate a contract and then open it up, and then take the values out of it, move them around, maybe mix and merge them together, and then lock them in a new contract. And this sequence of operations will be not just a list of them, but actually manipulating those values on the stack behind the scenes. So here's an example. Let's say you want to make a custom constraint to do something about it. So you start with pushing some numerical value on the stack, instantiate a variable out of it that creates the variable inside the constraint system. Then you combine different arithmetic operations on it that, as a side effect, create those constraints without actually computing anything, because the value could be encrypted. And you finish those constraints by saying verify, meaning that you compose the whole constraint and you want to record it into the constraint system, so it will be checked later. Then you can, so it looks something like this. So you have a formula and you do this kind of stack machine syntax for multiplying, adding, checking equality, and verifying. And then once you have this variable verified, you can create or borrow a value and output it in a certain place. So you say, okay, this value is correct, so I'm making a payment with it. And the borrow instruction is kind of cool because it's a zero interest rate borrowing. Just within the life of the VM, it gives you two values, the negative and the positive one, and the negative has to be mixed in with the proper payment coming from somewhere else using this zero knowledge mix instruction that we call cloak. It implements the whole cloak protocol that allows you to mix M inputs into N outputs, preserving the assets, but in complete zero knowledge. So you don't know where the asset flows within the boundaries of transaction. So these instructions kind of show you how you can combine the value flow with custom conditions. And the important part is that this is all imperative, meaning that all your contracts, they do not have kind of declarative conditions, but they imperatively do things that they want to be done with linear types that cannot be simply dropped or created out of nowhere or duplicated. So entire class of security vulnerabilities are eliminated. For instance, the access control lists always have this problem where you have hard time combining the different roles together. Here, it's very imperative, and linear types help greatly by just literally moving the value where it needs to be moved, and VM makes sure that you don't break the rules along the way. So this is very powerful, but at the same time, very safe system. So I'll say a couple of words about cryptography. So to make it all work, it's important to have, on one hand, fancy cryptography, but at the same time, pretty conservative one. So we have this stack of the high performance curve to 5519 implementation, on top of which we have the safe cryptography group, with which we built the bulletproof system that allows us to do these custom constraints. And we use the bulletproofs in two ways. In one way, it's a cloak protocol that enforces the network rules that mean that you cannot duplicate money. And at the same time, it allows you to do on-the-fly custom constraints. And this is cool because many other zero-knowledge systems like Zcash, they do not allow you to do on-the-fly conditions. Instead, they use a very complicated trusted setup where several parties must decide the rules and compute some, crunch some numbers in order to compose a single solid constraint system that will be used for all the purposes of the network for a long time. And bulletproofs allows us to avoid this trusted setup and instead build the constraints on the fly every time the transaction is running, because it's so fast and lightweight. And finally, to provide the interface to all of that, we have the ZkVM instructions. And then on top, with using these instructions, this is where you build your applications. And this whole stack that we have is written in pure Rust, so everything is very neatly compiled in one. First of all, it has all the nice APIs in between the layers, and then it's compiled without any overhead in a one highly efficient binary, just like you would have with the C++, for instance. So another cool thing is that the VM operations in ZkVM are designed to be either cheap or expensive, which is funny, but the point here is that the cheap operations are very cheap. It's really like a parser. And all expensive operations are completely uniform. Those are scalar point multiplications in this cryptographic group. And this means that they can all be deferred and done in a batch, which makes them much faster. So effectively, what you have is you have a very quick run of the program. Then you have a bunch of things to compute in a cryptographic group that you can batch together and do very efficiently. Later, you can even like imagine doing that in the GPU if you have to verify a lot of transactions. And then you have an answer whether the transaction is valid or not. So this gives us very low verification latency for the features that we have. It's less than 1 millisecond per output, so effectively like less than a millisecond per payment, or more like honestly speaking, it's maybe like 2 milliseconds per payment because payment also always have the change output. And we use all opportunities to improve performance that we can. So if you have multiple signatures, they all can be aggregated and then batch verified. And transaction size is pretty decent. So it's like 1.5 to 2 kilobytes, and this grows logarithmically. So if multiple parties join together, they greatly optimize the total cost of the network. And so a couple of examples how you can build something with this. So one is the basic payments. So the cool part is things like accounts and balances, they're all off-chain concepts. So the basic network only sees the inputs and outputs, and all the interesting kind of data wrangling happens off-chain that provides security for the people involved and for the parties transacting, and greatly improves performance because there's a lot of kind of complicated decision making is completely taken out of the consensus critical parts and placed inside the application. This also allows you to innovate faster because you can do different protocols and try different versions of like payment channels or payment protocols completely outside of the kind of consensus critical parts. So you have to only upgrade the nodes that care about this feature and not the entire network. So the order book is kind of an interesting example of a smart contract. So it's simply a contract that allows you to unlock the value being offered for price. So this is where you use the predicate and pack several conditions inside the predicate. And the cool thing about the zero knowledge is that you can do this both in the public, so it's like Stellar, like completely public offer, and there's nothing secret going on. But you can still do this kind of semi-public. So if you have a pool that wants to be kind of forced on the network and be auditable by authorized parties, but you don't want to publicize exact prices and exact assets that are being offered, then you can also do that as well, because all these formulas work on the encrypted values as well. And you can notice that this contract allows you to do imperative description of the conditions that you want to do. So you check that certain quantity and a price is moved to certain address, and then you unlock the asset that you have. You never have to do this kind of passive checks that whatever is provided or whatever like feature on a transaction object is set or some flags are set. For instance, in Bitcoin, there's very complicated kind of hashing flags. So there's none of those things. You can imperatively just do the things that have to happen. And then if there are some kind of negative amounts left in the stack in the VM, then the user has to provide appropriate amount of payment to cover them. And finally, payment channels is a nice example that shows you how to do complicated state machines in this model where you don't have global programmable state like in Ethereum. So payment channel naturally is a state machine between two parties that can do rapid payments without settling them on the network. And the only thing that network sees is that they initially deposit some money and then they close the channel at some point later. But all the intermediate movements of the money are not visible. But still, they have to provide some assurances to the parties involved. So how does it work? If the one party becomes unresponsive, then the latest signed agreement could be used as a way to exit the channel and settle by another party unilaterally. So this state machine is implemented on top of transactions. So the states are embedded in those contracts, and transitions are the transaction objects themselves, which is pretty natural. It's just the intermediately signed transactions, they are not published until you want to exit the channel. So this is how it looks in this model of inputs and outputs and transactions. Finally, to kind of wrap it up, a little comparison with other designs, and then we can proceed to the questions. So it's kind of like a setting for discussion later. So if you compare the design of ZkVM with Stellar, it's very different, but it's founded on similar principles. So it's a multi-asset environment for modern financial protocols. And the specific difference is that the data and asset values are confidential and encrypted by default, and you can of course make them public if you want to, and do any sort of conditional or conditional disclosure schemes if you need some audit. The concept of accounts is completely off-chain, and the verification of transactions is largely stateless. And your mechanism for customization is this composable instructions instead of just an enumeration of kind of thicker, higher level operations. And another important difference is that the order book logic in Stellar is built in and has some kind of stateful conditions that allow for more interesting kind of multi-party price assurances. In ZkVM, there is no such built-in concept. You can build all sorts of order books on top of the system yourself, depending on like how complicated you want it to be. Compared to Ethereum, Ethereum is also designed for the customization and smart contracts, but the model is quite different. The Ethereum is sort of like a global state machine with a lot of code and like libraries of code that can call each other and do a lot of stateful changes. In ZkVM, all the changes are isolated and limited to this creation and deletion of the outputs. And another important part is that ZkVM is not Turing complete by design. So it really acts more like a parser and allows just as little composition between the instructions and data as necessary to to create useful financial operations, but not to just program whatever. And the assets are first-class types that you can move directly around instead of being some entries in a miniature bank that you have to program inside your program inside Ethereum. So this makes the whole design much more easier to reason about, because you don't have to reinvent a little ledger inside the ledger every time you want to create a new asset. And finally, Zcash and Monero, they are heavily focused on the privacy, and they provide some cool non-interactive obfuscation of the transaction graph, which ZkVM does not provide, but you can still do this with schemes like CoinJoin. So when multiple people join multiple inputs in one transaction, then they can sort of mix them. But ZkVM provides you with ability to have customization in contracts, where Zcash and Monero doesn't have any. And still even have the confidential computation within those contracts. And finally, yeah, Zcash and Monero have single asset, and ZkVM is designed for multiple assets. So as a summary, what we're having here is this experiment in combining customization, confidentiality, and scalability features in a single project, and using to the optimal degree all the latest inventions in the blockchain space, where we have reasonably innovative cryptography, but still trying to be on a conservative side, and trying to make things very scalable and high performance. And obviously pushing as much as possible to the off-chain application design, so we can innovate faster and have the core consensus critical parts as simple as possible. So that's all I got for my talk today, and then we can transition to questions. You can check out the demo at zkvm-demo.stellar.org, and there is a Stellar/Slingshot repository on GitHub where all the discussion and design work is happening daily. Thank you. Oh, yeah. So we received some questions. So the first question is, can the ZkVM logs be applied to the Stellar blockchain, or is it a separate sidechain? The ZkVM blockchain is an entirely separate system that can work as a sidechain, or can work complementary. It can work as a sidechain complementary to Stellar. So you could have a set of validators overlapping both systems and using the same Stellar consensus protocol. So they can operate in parallel. And we have some thoughts on how to do the import-export mechanism for the Stellar assets from the main chain into the ZkVM sidechain. At the same time, and the similar mechanism can be used for the ZkVM in private setting. Let's say you have a organization where you need a robust internal ledger that is cryptographically assured and limits the information exposure. And you would like to use it internally, but also interoperate with Stellar. So that's also a good idea, because then you can protect your internal data from your own system administrators and your IT department, so you can more precisely specify who sees what information if you run the ZkVM blockchain just as your internal private ledger. The second question is, can you build an automated node for collateralized loan? How would you invoke locking for deposits, and is there an opcode, or do you require an operator in between? So this is a cool question, because a collateralized loan is one of those things that you can naturally build with ZkVM instruction set. So you could make an agreement that the person receives, the creditor receives the money if they lock some digital asset as a collateral. And this lock will have a custom predicate that allows you to take it out of the, allows the creditor to take out the loan after some timeout, and also allows the person who takes the loan to unlock the collateral provided they make a payment. And the contract, the predicate of the contract will have a provisionary formula to check that the payment was done, including whatever required interest rate before the timeout. So this scheme requires you to build a little bit of this kind of smart contract program to embed in a transaction and build some infrastructure around to kind of support it in the wallets to use this feature. But then it provides both parties with security against each other. They can simply unlock the collateral with mutual agreement, but if they disagree or don't cooperate, then each party has a clause that protects them from another. So the creditor is assured that after a timeout, they can simply take the collateral and sell it on the market, and the debtor is assured that they don't need to cooperate with the creditor. They can simply take back the loan, to take back the collateral, provided they pay out the loan to a predefined address. So that's a kind of perfect example for the use of ZkVM. And you don't need any third party to intermediate these transactions. So it's fully like just two parties and without any trusted third party to mediate them. Are you able to provide a timeline for when you expect ZkVM to be fully complete and live on Stellar? So that's a trick question because the ZkVM itself is pretty complete. What's required, which is a kind of like annoying engineering problem, is to build this kind of blockchain kind of networking infrastructure around it, so you could integrate it just with the kind of networking nodes, which is an ongoing problem right now. Like we have the blockchain state machine, we have the like peer-to-peer network components, but there is also all the kind of wiring, like the packaging up a node with the UI and stuff and things like that. But also there is the integration with the Stellar consensus protocol and integration with the Stellar assets that are two separate problems. So so far, I would like to have it as soon as possible, but we're kind of getting out of the stage where we have to build something within this kind of Slingshot project, and now it's kind of in the last in the ongoing weeks, we're going to really face the problem of integrating with Stellar consensus protocol and with Horizon and with like import of the assets. So we're working on the roadmap for this right now. So this will require not just kind of work on the project itself, but more like integration work and working with more engineers on the Stellar kind of broader Stellar side. So the roadmap is being in development right now. Do we have any more questions? Well, thanks everyone for joining us today. We're glad you've watched this live stream, and if you would like to participate in the project and have questions, would like to integrate things with your applications, then please find the GitHub repository, which is stellar/slingshot, and I would be glad to see your issues or pull requests. So Thank you so much.